So today I'll be talking about biomechanics in regards with linear motion for athletes. The first aspect of linear motion is linear motion itself. This is where an athlete or an object performs in a straight or a curved line. An athlete performing an event in a straight line is the 100 meter sprint. This is an example of an athlete performing rectilinear motion. As the 100 meter track is a solid 100 meter straight, they'll only be moving in one direction throughout the whole entire course of the race. The other aspect of linear motion is whilst it is performed on a curve or at a curved line. This is known as curvilinear motion. This is when an athlete or an object will change direction over the course of what they're trying to sustain. An example of an athlete performing curvilinear motion is the 400 meter sprint. As the athlete will be consistently changing direction and changing angle at the curves and the bends in the track, they won't be moving in a sustained direction of movement at any one point. The other example of when an object is moving in a specific direction whilst curving is when a footballer is trying to take a free kick. As they will be looking to put curl on the ball to try and put it around the wall, the football will change direction in the player's attempt to try and score. Moving on is pure and non-linear motion. Pure linear motion is the movement of the body in one direction, moving at a constant speed. An example of this is when Bolt, as he runs down the 100 meter track, as he will only be moving in one direction in order to try and win the race. Following on from that, there is non-linear motion. This is when the body is not following any sort of specific movement or motion patterns. The body will be consistently changing in multiple directions due to the purpose of the sport. A good example of this is boxing, as boxers will be consistently trying to evade punches and throw punches themselves without the other boxer not being able to read what they're trying to do. There'll be lots of different feints and motions, and no specific direction of motion will be taking place throughout the sport. Moving on from that, you have scalar and vector quantities. Vector quantity is measured in both magnitude and direction, whereas on the other hand, a scalar quantity is only measured purely by its magnitude. Displacement is a vector quantity as it is measured by both magnitude and direction, which is the difference between the start and the finish point of either an object or an athlete. Contrastingly, a scalar quantity is only measured by its magnitude, which is the distance travelled by the athlete at any one point. Another example of vector quantity is weight. Weight is a vector quantity and is solely measured in newtons, which can be represented by the N symbol. On the other hand, another example of a scalar quantity is mass. Mass is measured using kilograms, which can be shown with the symbol kg. Moving on, you've got two separate topics in regards with speed, velocity, acceleration and deceleration. Speed is defined of how quickly something has moved from the start to an end point. This is measured in meters per second. The equation for this is distance covered in meters divided by the time taken in seconds. So an example of this is a 400 meter runner who runs the course of the track at 50 seconds. If you were to take the distance that they've ran by the distance that they took, it would have taken them 8 meters a second to complete the race. Velocity is defined as the change of position and the amount of seconds that this change took to occur. If you were to take the same example of a 400 meter runner, they would have run the course of the track but ended up in the same start and end position, so their displacement in meters would have been naught, and the time taken would have been 50 seconds. So if you were to take their displacement in meters and the time taken in seconds, you would have ended up with a displacement or velocity of 0 meters per second. On the other hand, you have acceleration and deceleration. Acceleration measures the change of something's velocity over a set period of time, and this is measured in meters per second squared. The acceleration equation can be shown with the final velocity minus the initial velocity divided by the time taken. So an example of this for a 100-meter sprinter is if they've completed the race in 10 seconds, their final velocity minus their initial velocity would be 10 meters per second, because 100 divided by 10 would equal 10 meters per second. So that's what it would be at the end of the race. The initial velocity would be 0, because at the point at which the starting gun goes, they wouldn't have any velocity behind them. So if you take 10 minus 0, that would equal 10 meters per second. And then, as it's taken them 10 seconds to complete the course of the race, their acceleration over the course of the race would be a sustained 1 meter per second. The deceleration, this is exactly the same, however, it is the negative acceleration of something over a period of time. This is used to measure the reduction in speed, and it is measured in meters per second minus 2 squared. From then on, you have momentum. Momentum is the quantity of motion that something will possess, and this depends on its mass and velocity. The equation for momentum is mass in kilograms times its velocity in meters squared, and that would equal momentum in kilograms per meter squared. If you were to have an example of that, it would be the momentum of a bowling ball being bowled. If the mass of the bowling ball is equal to 7 kilograms and the velocity that is being thrown at is 6 meters per second, you would have to work the equation as 7 kilograms times 6 meters per second, giving you a momentum behind the bowling ball of 42 kilograms per meter second. The next aspect of this is I'm going to be analysing Usain Bolt versus Tyson Gay's 100 meters in 2009, in which Usain Bolt broke the world record. During the speed of which Bolt took to run the whole course of the 100 meters was 9.58 seconds, as we can see down here at the bottom. Broken down, it is into 20 meters periods, so the initial 0 to 20 took Bolt 20 meters divided by 2.89 seconds of 6.92 meters per second. The following 20 meters after that were 20 meters divided by 1.75 seconds, giving him a greater speed of 11.42 meters per second. As we reach the midpoint of the race, the 40 to 60 meter section, that 20 meters would be 20 meters divided by 1.67 seconds, giving him a furthermore increased speed of 11.97 meters per second. After that is the 60 to 80 meter section. This is the next 20 meters, so 20 meters divided by 1.61 seconds, giving him a speed of 12.42 meters per second, which is quickest over the course of the race and the quickest over the course of any athlete performing that race. And then the final section of Usain Bolt's speed is the last 20 meters. So 20 meters divided by 1.6 seconds is 12.04 meters per second. This shows us that he slowed down towards the end of the race. Moving on from there, you have his velocity. As the velocity